Hello everyone, today is an exciting day because we are beginning double integrals and like all the integrals we're going to do in all the different coordinate systems. My DiffEq is starting next week, so I know I've been slacking off with the uploads. I've just been having a pretty busy week. I've been looking at DiffEq for next week. I've been doing surf. But at least these videos are exciting, so I'm a bit more motivated to do them. Okay, so in particular, we're going to be doing double integrals in rectangular regions. Okay, so I guess we can kind of start off with the, we look at what was happening in Calc 1. In Calc 1, you got an arbitrary curve and you want to find the area underneath this section from A to B. You can do that with itty-bitty rectangles, right? So you got all these rectangles and you're approximating area. And then you're taking the area of each of these little rectangles and you're adding it up, and that's approximately the area under the curve. So what that is, it's a sum, right? From I equals 1 to n rectangles of f of xi times delta x, right? This is the width down here. Then f of xi is the height. Okay? And you're adding n rectangles. Now you can turn this into an integral by adding a limit here. Limit as n approaches infinity. What this is doing is it's making the number of rectangles become infinite. Okay, so this is an integral from a to b of f of x times dx. So yeah, you have infinite like thin rectangles and you're adding them up. Okay, now there's a similar definition for double integrals in 3D where if you have like this and then you have some kind of arbitrary surface up here and you were interested in this rectangular region, you could piece it out like this. Sorry, hold on, let's say goodbye to Discord real quick. Okay, yeah, so say you pieced it out into those kinds of sections. You could put a rectangular prism into each of those guys. And then, add these guys up. This is not a very good drawing, but you get the idea, right? Maybe if I look up double integral visualization, we'll probably get something nice looking. Yeah, okay, so like, let's change the color of this. Is kind of ugly. Okay, yeah, so like something like this. And you could increase the number of these rectangular prisms you have and it'll be more accurate. But this is what I'm trying to draw. This is an upside down paraboloid kind of, and well, it is, and you're approximating with the volumes of these rectangular prisms. So it's pretty much a direct translation from 2D to 3D, area to volume, right? And then what the definition for this guy, you don't need to know how to do these for the class. It's just kind of, I guess it's standard to look at where it comes from. But it's literally just a double sum. So it would be the limit as m comma n approach infinity, and the sum of I equals 1 to n, and then the sum of j equals 1 to m of f of xi comma yi times delta y delta x, or delta x delta y. You could also rewrite this as delta a, because you have a little change in, so if this is y, this is x, this is z. If you have a little change in x, so call that delta x, and then you have a little change in y, and you multiply them, you're going to get the area of a little change in area. So that's why you could call them that. So you would write a double integral like this, like a to b, assuming a and b are constants, same with c and d right here, and then f of x comma y dx dy, or as I previously stated, dA. Okay. Now, with rectangular regions, it's important to note that you can swap these integrals. So I guess before I move on to that, how you do these is you integrate this first, what's in here first, and then whatever you get out of there, you integrate from a to b with respect to y. Okay? So knowing that, you could switch these guys around, and then you could also switch these guys around if it's a rectangular region. So this is going to be equivalent to integral from c to d, and then the integral from a to b, f of xy dy dx. And again, you would do the dy integral first this time, and then the dx. Okay, so an example I want to do with you guys is here. So we're going to go from 0 to 2 and then 0 to 1 for 1 minus x minus y, and then dy dx. Okay? So this is the function we're integrating the volume for. We could kind of visualize this. So that's just a plane, right? So his intercepts are all 1. So he's something like that. And then in the x direction, we're going from 0 to 2. So I don't know, somewhere around here. You could imagine it's extends a bit further, and then y goes till 1, so till there. And yeah, this is kind of the region we're integrating. And you're, oops, sorry, it should be down there. And if you looked at this from the top, it should just be a square. So here I could maybe even open up Desmos 3D, and we could get a better picture of this. So we have 1 minus x minus y, and we want x to sit from 0 to 2. And then we want y to sit from 0 to 1. Yeah, so that's our region. Well, that's the plane actually from the top, but you could see that it's a rectangular region, right? And that's the plane. So what we should expect, honestly, is if we hit him with a z equals 0, so above here, above z equals 0, right, this is going to be positive volume. We're going to get some positive volume, and then down here, we're going to get negative volume, okay? So we see that we're going to have way more negative volume. I don't know about way more, but we're going to have more negative volume than positive volume. So we should expect our answer to be negative here. Okay, so let's start this off. So like we said, we're going to start with the innermost integral. So what is that? Integral of 1 with respect to y is just, oh wait, let's do it separately. So this guy is what we're going to integrate for now, and that's going to be y minus xy, I'll get back to that in a second, minus half y squared from 0 to 1. Okay, now the reason we hit them with an xy is what's happening here is, so we're integrating in the y direction, right? That direction over there. And this, so, and then this is a function of x comma y, right? I guess maybe it's, I'll just call it z. This is z, okay? You can compare this to how in single variable, if you have, I don't know, a to b of y, which is a function of x implicitly, with respect to x, this integral is in the xy plane, okay? So this integral is going to be in the yz plane, okay? So if we look at our yz plane, maybe even in this photo right here, this is going to give us a function for the area of any cross section, okay? So when we say x is a constant, right, that means x could be a, okay? And if we plugged in a certain a value into this function and we were like, that means we would be slicing this with x equals a, and we're going to be like, okay, in this cross section, what is the area of that shape, okay? And this is going to include both the top side and the bottom side, okay? So I guess basically the gist of it is, when we're doing this, we're integrating in the yz plane, and so we treat x as a constant, okay? And when we do that, we're going to get a function that's going to give us the area of any little one of these pieces at each like slice of this pyramid thing that's on the x, that's a constant, that's at a constant x value, okay? So I guess if you could visualize it like this, like, okay, this slice is at x equals 0, okay, and then you have another slice, maybe slightly smaller, this one's at, I don't know, x equals 1, okay, and then you stack them all up, and you're gonna get that curve right there, that kind of tetrahedron. Maybe not the best drawing, but you do have all these cross sections of right triangles, okay? So, I don't know, say that's our first one. This is our second cross section, third, till infinity, and then you stack them all up, and you're gonna get this tetrahedron thing. Okay, so now we integrate from 0 to 1. Now remember, these are y values. So we're going to plug them in for y. So we're going to get 1 minus y minus half. If we plug in 0, you're just going to get, oh, sorry, this is x. If you plug in 0, you're going to get 0 for all of them. So then this equals half minus x, okay? So at any slice here, the area is going to be half minus x, okay? So, for instance, if we said x equals 3, or, okay, well, that's past our margin. We'll say x equals 1. That's solid. So, yeah. So we're going to have some triangles here. Yeah. So at x equals 1, we have these, like this, we're only going to have a negative triangle, if you notice that. Okay? And that, honestly, that does make quite some sense. At x equals 1, if we do half minus 1, we're going to get negative half, which is a negative value as we expect. And also, if we really wanted to, we could also compute the we could hand do this because we can do this by hand because these are just triangles. But you could figure that out yourself. You would just see what you'd plug in. What is it? X equals 1 into here. You would see what line that makes in the YZ plane. Find the area. Honestly, we could even do it right now. So X equals 1. Okay, so that means Z is going to equal, what is that, negative Y. So if we're sitting in the YZ plane, Z equals negative Y. This is Y, this is Z. So what is that? That's like that. Okay, and we're integrating from 0 to 1 in the Y. 0 to 1 of negative Y dy. Okay, so this is the integral we have. You're going to get negative half y squared from 0 to 1. And then you could see that this is negative half, which we got back here as well. Alternatively, you could also just say, oh, this is y equals 1. And then, okay, and then have this height. That means this is also 1. Well, it's negative 1, right? Because you're going downward. So base times height divided by 2, that's negative 1 over 2. Okay, so 3 different ways we did this, and we got the same answer. So this, at a constant x value, this formula, after the innermost iterated integral, this is going to give you a formula for at a constant x value, oh, what is the area at that cross section? Okay, so if this first step, this innermost iterated integral, right, we call these iterated integrals, if the first step to that is getting this formula for the area of each little cross section in a certain direction, in this case the y direction, well, I guess it's in the x direction because we're moving this guy that way, then what is the next step? Okay, well, let's look at it. So now out of this we got half minus x. So this is where we'll do our next integral. So we got half minus x dx. Okay, so this guy is any triangle from x is 0 to x equals 2. Okay, and we know that all of these guys are right triangles because we could, kind of analyze this photo. Okay, so what we're doing to each of these guys is we're multiplying them by dx. Okay, so initially we had this flat guy, but now we have a triangle. Oops. And he's got a thickness. Okay, holy shit, I'm so bad at drawing. So he's got a thickness now. Wow. Okay, and this is supposed to be its thickness. Its thickness is dx, and his area is half minus x. This isn't completely accurate because you can have triangles on the top and the bottom, but just for visualization sake, this is what we have. We have an area of half minus x, and we're giving them a thickness of dx. Okay, so what this integral is saying is add up all of these volumes from 0 to 2. Okay, so you could see this pretty easily. You're going to half x minus half x squared from 0 to 2, and then you're going to get, if you plug that in, what is that? That's going to be 1 minus 2 minus 0, right? Because we plug in 0. So this is negative 1, okay? The whole volume under the curve, it's a surface, in this rectangular region is negative 1, okay? Okay, all right. So that's the first example. Now next example. Let's see, what could we do? Or should we jump to the? Well, okay. Let's actually do this example. This is actually a past test question. but I think it's important to know. So you have a double integral 0 to pi of, let's maybe even zoom into this, of cosine x plus y dy dx. Okay, how can you integrate this? You know, we could actually implement these past exam problems as part of the lesson, so we don't have to do them at the end. But okay, so yeah, how would you do this? Well, you can u sub, because remember, we're in this integral right now, we're in dy. We're going to treat x as a constant, right? Because we're looking at a cross section at x equals a being a constant. So you could hit them with u equals x plus y, du equals dx. Okay, now don't forget that your bounds are going to change. Okay, so I'm only going to rewrite the innermost integral after the u sub. Now keep in mind we're in the y integral, so these guys are y values. Okay, so that means over here we have x plus y. So that means the bottom one is going to be x plus 0, so x. The top one is going to be x plus pi, okay? Or pi plus x, whatever. All right, and then we replaced x plus y with u. And then we got du, because du equals dx. Okay, and then let's move back here. All right, we know the integral of cosine of u is sine u. You know, it might even be easier to replace it back with, well, actually, whatever. Okay, so now we have sine u, and he's going from x to pi plus x. So the innermost integral, we have this. Okay. So that's that innermost integral. That means now we have another step. We have another integral to do. So this one's also from 0 to pi. And it's from sine of pi plus x minus sine x in dx now, right? We just replaced what's in this parentheses with this guy because we solved it. Okay, well, we could figure this out. Integral of sine is negative cosine, right? Because taking the derivative of cosine gives you negative sine, so you need a negative to make it positive. Okay, yeah, so this is going to be negative cosine of pi plus x. This is basically what we did back here, except this is a well-known constant, so I don't have to explain that you could u sub this. Okay, and then this is just negative sine x, so that's going to be plus cosine x. And this is going to go from 0 to pi. I think the final answer for this should be negative 2. Okay, so we're going to move on to the next line. I know I moved you just to see what I had written down, but okay. So yeah, so now I'm just going to rewrite what I just wrote, just so you could see it all on the same line. Okay, so that's what we had. Now you're going to have negative cosine of 2 pi plus cosine of pi minus negative cosine of pi plus, plus cosine of 0. Okay. So I'm going to actually zoom out because it's getting hard to see. Okay. So now we're going to move on to our next line. So what is this guy? Negative cosine of 2 pi, that's negative 1. Cosine of pi is negative 1. And that's minus. Cosine of pi is negative 1. Cosine of 0 is 1. So that means these guys cancel. And you're going to have negative 2 minus 0, which is just negative 2. Yep, that's the answer. And keep in mind, since this is a rectangular region, you can also just swap dx and dy, but it's going to be the same exact thing, same exact kind of process, but you'll get the same answer. Okay. Another example we could do, I did it earlier, just kind of forgot what it looked like. Where did it go? Okay, this guy. 0 to 1, 0 to 4, dx dy. Okay. Okay, so this is also a past test question. So this one, 0 to 1, 0 to 4 of root xy dx dy, I believe. Let me double check that. Yep. Okay, so we should get 32 over 9 at the end of this, remember that. Okay, let's solve him. All right, so here, this is another little tip. Yes, you can U-sub like we did previously, because they're kind of tacked onto each other. Actually, well, will it be that useful? I don't think you should U-sub. But what you can notice is that these are both definite bounds, and these could be written as a product of two things, right? One being root x and the other being root y. Okay, what is that? How does that benefit us? What you can actually do is you could split the integrals. So you're going to shove this guy into dx. You're going to shove this guy into dy. Okay, so if we put the first guy into dx, we have 0 to 4 of root x dx. And then, like we said, we're going to shove the other guy into dy. So 0 to 1 root of y dy. And the reason you can do that is, so if you rewrite it this way, you realize that, so I guess, okay, we'll start from inside out. You realize that, okay, hold on, maybe I have to rewrite this in the other form just to make it easier to see. Yeah, so this is our first integral. So if we look at the inside, we're integrating an x. X is the variable, y is a constant. You can factor him out. Okay? So that's going to give you the root of y. Okay, so then what that's going to give you is it's going to be 0 to 1 root of y times the integral of 0 to 4 times root x dx dy, okay? Now, what that now means is, what are you going to get out of this? A constant, right? So you could take this guy out of here, and you're going to have 0 to 4 root x dx, because that's a constant, times the integral 0 to 1 of root of y dy. That's why you could do that. And it's honestly pretty helpful. Okay, so now that we know that, and we proved it, we know that, well, if you have something to the half, that's going to turn into x to the 3 halves, 2x over 3. Okay, yeah. 2x 3 halves over 3 from 0 to 4. Okay, that's this integral. And then this guy's going to be pretty similar. 2y 3 halves over 3 from 0 to 1. Okay, so this first guy, what is that? 4 to the 3 halves. That's root of 4 cubed. 4 cubed is 64. Root of 64 is 8. So you're going to have 2/3 times 8 and then minus 0 times that, so that we don't care about that. And then plug in a 1, you're going to have 2/3. Okay, so this is going to give you 2 times 8 is 16, times 2 is 32, and then 3 times 3 is 9. So yeah, okay, 32 over 9. All right, so that's the double integral part. Okay, well, actually, the next part is also double integral for this video, but it's expanding on something that was also in Calc 1, which is average value of a function. So something interesting I actually learned while doing this that I never understood this till I actually looked this up for the video. But in Calc 1, you know that the average value of a function, f average, is 1 over b minus a times the integral of f of x dx from a to b. This is Calc 1, right? And the reason is, I guess, a geometric way that I found was if you have an interval from a to b, and then f average is a constant, right? So suppose this value right here is f average. Then the area in here, so this has a width of b minus a, and then it has a height of b minus a, and then a width of f average. This is equal to the integral from a to b of f of x dx. And yeah, so if you want to find f average, you just divide b minus a by both sides. That's how you get that. And yeah, I found this on multiple sources. I think 3 Blue 1 Brown made a pretty different case that was also really interesting, but I can't quite remember it. But I found this one on Chenflix and some other source online, so I thought this was kind of interesting. Okay, but the Calc 3 version is basically the same thing, except your region isn't a length, it's an area. So it's pretty similar. That means if you have a triangle, or oh my god, this area down here with area A, and then it goes up to, what is it, to z equals f average, then the volume in here, so the volume in there is going to be f average times the area down here, is just the double integral from a to b, from c to d, of f of xy dy dx, right? So same kind of idea, just divide a by both sides. Okay, and that's how you get that. I don't think you need an example with this. It's literally the same as before, except you divide by the area. Okay, now I suppose, oh, there's another example we could do. I found the problem. Yep, we're on our last page. It's not really even a page anymore. But notice that here, if you do it in this order, dx dy rather than dy dx, you're going to have to use integration by parts, right? Because it's a product of x and e to the xy. Y is a constant, and we don't want to do integration by parts. I don't think a single time in MA 261 I ever used integration by parts. So what do? We just switch the order. So this is still equal to 0 to 1, 0 to 1, because it's a rectangular region, x e to the xy dy dx this time, okay? So now we're going to treat x as a constant. Okay, just for starters, we're going to pull this x out here, just because we don't really mess with him. And then you're going to get, you can integrate this 0 to 1, e to the xy, so this is just e to the y times a constant. Now if you take the derivative of that, well, I think it's going to be e to the, hold on, it's going to be e to the xy. if you take the derivative of this guy, you're going to get e to the xy times x. So you're going to have to divide by x in this, right? Okay, so then it cancels out with whenever you take the derivative. Okay, and then you got them going from 0 to 1. And these are y values, right? Because we're integrating in the y. Okay, so this equals e to the x over x minus e to the 0, which is 1 over x. Okay, so we put them in here. Now what's really nice is you multiply this out, it's going to cancel. So now you have the integral of e to the x minus 1 from 0 to 1. And then this is just e to the x minus x from 0 to 1, which is e minus 1 minus 1. So this is just e minus 2. Okay. So yeah, if you do it one way, you can avoid integration by parts and get this really nice little cancellation right here. If you want to do it with integration by parts, do that. I'm not going to do that in this video. I'm good. All right, that's all I have for today's video. I did implement the some of the test problems throughout the video as example problems. If you need me to do more example problems, that's completely fine. I could do that. Just send me, or just comment it. I'm hoping that in the fall, I'm going to be tutoring. I'm going to be at the ASC in Purdue Indy, and as a tutor, and hopefully I could recommend my videos to some of my students, and they could give feedback, because no one's commenting on these. But I suppose it's summer, not many people are taking a class. Not even oh well. Anyhow. All right. But yeah, leave comments if you're able to, and I'll see you guys in the next one when we're gonna do double integrals on general regions. Bye.